Okay, this question comes from June 2010, and this is the first of the new specification questions. So it's question 7 on nuclear fusion. And first question is asking for us to sketch the binding energy per nucleon versus mass number curve. And this is very important now because we have 240 along here, so 240, that's going to be 120 here, so that there's around about 60. So the examiner is looking for it to peak around about there, so it's going to peak somewhere around about there, and at 240 it comes down to about 7.5. so we're looking for a curve which is coming up very steeply, peaking there and then going down to somewhere there. So these 2 points are important because the examiner is looking for it to peak at 8.8 and 7.5, and remember it goes up very quickly to there and then comes down. What is meant by the expression binding energy per nucleon? Well, that's the average energy needed. Okay, so it's the average energy required or needed. And what's it required to do? Well, it's to completely remove a single nucleon from its nucleus. So it's the energy required to completely remove a single nucleon from its nucleus. So it's the energy required to remove a single nucleon from the nucleus. Fission and fusion then, our nuclear processes give out energy. State how they differ in terms of the nuclei involved and what happens to those. Well, it's a 2-mark question, so not a great deal of detail required here, so we have to say what each of them is. So fission then is a splitting of a single heavy nucleus into 2 smaller nuclei. And what is fusion? Well, fusion is the joining of 2 like nuclei into a single heavier nucleus, or into a single nucleus really. Then, with reference to the graph drawn, explain how both nuclear fusion and fusion can liberate energy. Well, energy is released when the binding energy per nucleon increases. So whenever they increase the binding energy per nucleon, then what happens there is energy is released. So whenever you fuse together to something which is down here to become something here, you've increased its binding energy per nucleon. The same, something which undergoes fission from here to here, it increases its binding energy per nucleon. So that's the first point that we have to say, is energy is released or energy is liberated when the binding energy per nucleon is increased. And both fusion and fission increase the binding energy per nucleon. So energy is released. So it's fairly straightforward. Increase the binding energy per nucleon, releases energy. Fusion does it, fission does it, and if you look back at the graph, you'll see going from there to there, greater binding energy per nucleon, going from there to there, greater binding energy per nucleon. Then the final question, explain why the energy given out per nucleon from fusion is greater than that from fission, and that is because on the graph there is a greater increase in binding energy per nucleon for fusion compared to fission. And again, look back at the thing. You're going from, in fusion, you're going from here to here, so it's a jump of that, whereas in fission you're going from here to here, so there's a much smaller jump in this area than there is in this. So fission gives less increase in binding energy per nucleon than fusion.